Hello everyone, so today I'd like to talk about my project of the class Deep Learning 435 in this video. And so my project is basically based on the prediction of chemical properties using only the elemental fraction. So this topic, the reason I choose this topic is because nowadays you have a lot of data sets, like you have like compound and you have the properties related to it like band gap, formation energy, and a lot of stuff. But usually for domain scientists, they uses like a lot of physical data in order to predict the properties, and you have a lot of them, and you like for even for some data you don't even have the physical properties, and it takes a lot of time to calculate each and every one of the physical properties if you are trying to predict something out of it. So in order to make things easy for them, as a new input for the neural system, the elemental fraction is chosen as like the input in order to predict the properties. Like even though you have like some basic errors, but you are able to produce a near same effect or like the near same value for the same chemical property that you're trying to find with much less effort, because the chemical composition is already available. And if you have the chemical composition of an unknown compound, you can just put that compound in the neural network and you can predict the almost like similar value for the property that you're trying to predict. So there are a few problems that I faced while trying to make this thing. So first thing is like to acquire the data set. There are a lot of data sets, so I'll use OQMD data set that contains like right now more than 600,000 chemical compounds and properties related to it. And the second problem that I arrived is that how do you convert like the chemical compound into the array that you are going to use as an input for the neural network. So in the case where I did was I like tried to create a function that could convert, even if you have the bracket, you are able to convert that thing into a normalized input vector for the neural machine. The third thing that the problem that I faced is like what kind of neural network would be good in order to provide or to give a good accuracy. So in this project, I basically use fully connected layers, and I just tweak the number of inputs for each of the layers and number of layers in order to check which would give me like kind of the good results as compared to the conventional machine learning models. So in order to compare it with the conventional machine learning model, I also checked a lot of conventional machine learning models to prove that the neural network, the deep neural network that I'm trying to implement, performs better than all the conventional models. And after being able to like produce a decent layer or the decent neural network, I tried to test it on different kind of activation function optimization, and like by increasing the layers and all those stuff in order to see which optimization and the activation function would provide me with the best results. And also, like, just to give you a quick idea about what a fully connected layer is just like neurons connected like in a horizontal way. Like you define each of the layer dense networks for the fully connected layer, and they connect to each other, and you have input, you have output, and you have like a lot of layers in between. They are connected to each other, and they will just tune themselves as they get the input at every batch size, and that's how they train the network. So like after performing the experiment for like few weeks or like almost like more than a month, I was able to reach at a conclusion that like around like 17, 18, like 16, like around that area, like for the OQM data set, that number of layers would perform and give you a like one of the best results that I could get after the experiments. Also, like if you don't have a dropout in between, it will also give you a better best results. Along with that, the best optimizer was Adam, that's the widely used optimizer, and the activation function was ReLU. Also, that's like one of the best like the activation function that you have right now. So that's how it turned out to be, and it like compared to the conventional model, it gave you very low like error. Like I used the mean absolute error for this experiment. It gave you a very low error for that, and also it only uses elemental fraction as an input, so it's an easy to create network. So you don't have much of the data, you just need the property and the compound name. With this, I hope that like I still haven't tried a lot of layers, so if we try a lot, we may able to decrease the error by a lot more. And with this, like we can even try to predict the properties of newly like the elements we don't know the properties of. Also, I was able to get a lot better result than already existing things, so that proves that like I did quite some work in order to like find which will give me the best results.